So this is the LLM 101 session, and we are going to take a brisk look at large language models, and we're going to do so in kind of a hopefully fun and interesting approach. So let's talk about what is involved in taking an algorithm and turning it into a model, right? And actually taking the code and then building all these weights out so that we actually have something that's useful. In the first step, we need to get a massive corpus of data. So this is why most companies don't pre-train their systems. Most companies and most developers are going to find a open source, open weight model, and they're going to download pre-trained weights. And so lots of organizations provide weights for their models that are available, and you could just download them. The challenge is you don't know what data they were trained on. There's there's some of that. Some system, I take it back. Some open source models with open weights do say, hey, this is the web download stuff that we used, and this is the book repository of all the books that we trained it on, and so on. But for the most part, like Meta, you can use their Llama LLM, which is fantastic, but they're not going to tell you exactly all the data set that they used and that sort of stuff. So if you wanted to do it yourself, you could collect your own data and you could pre-train your model like we're doing, right, from scratch. Next thing that you need is tokenization. So models are just math, right? Matrix multiplication, stuff like that, right? We're just taking these weights and we're tweaking them, and it's very complex and there's a lot of it. But at the end of the day, it's just math, and some of it's linear, some of it's nonlinear, and this is how we get these interesting and very impressive next token generation sequences that make it seem like the model is actually thinking or smart, but of course, if you don't ask it a question, it just sits there. It's a piece of software. So tokenization is how we take text, English language, Swahili, Chinese, any language, and turn it into numbers so that the LLM can ingest it and process it. And there are lots of different tokenizers that you can build. We built a really simple one. Next, we've got the transformer architecture. And so this involves two main components, the feed-forward network part and the attention part, and we'll talk about those. And then there's the supervised learning. So how is the system learning from this data? Well, what it's doing is it's looking at the documents in phases. And so if there's a piece of the document where there's, I want to ride my, it'll look at that and it'll try to figure out what the next token is. And then after it's figured it out, it'll look at what the next token really was. And then it's going to figure out how to move all of the weights in the system to make it slightly more likely that that's the token that would be picked. You don't want it to just lock in, because then your model becomes one-dimensional, right? The only thing it can ever do when encountering this kind of text would be assume bicycle, right? We want generalization. So for example, let's say you meet your friend Bob, and Bob's had or let's say it's not your friend. You meet this guy for the first time. Bob's had a really bad day. Bob's kind of grumpy. Well, do you just assume that Bob's a jerk and is grumpy all the time? Or do you recognize the fact that perhaps, Bob's had a rough day and maybe tomorrow Bob will be, happier or friendlier or something, right? You probably do that. And next thing you know, you meet Bob again and Bob's nice. It's the same thing with the model, right? We don't want the model to get hung up on, this exact pattern is always this. We want it to be able to generalize. We want it to be able to look at context. We want it to be able to have a deeper understanding of the language. And so we don't want to essentially overfit. And so we need a way of providing lots and lots of information to the model so that it can see all sorts of different contexts and capture lots of different ideas and things like that. So this self-supervised learning process is really important, because if you had that much data collected and then you tried to somehow or another create the right answers for different situations in a manual fashion, that would be really expensive and time consuming. Now, people do that for the later parts of fine tuning in many cases, but in our situation, we want self-supervised learning. So the system is just looking at the documents and blocking off, the half that it's not supposed to look at, and then predicting that next token and then seeing if it was right and learning from that. So that's self-supervised learning. So we do this, for, in our case, a minute. In the real world, we would do this for hours, days, weeks, months even. and in massively parallel scenarios with lots of different GPUs and so on. And at the end of the day, you now have a general purpose model like we do. Well, we have a general purpose Shakespearean model, I guess. So that's our pre-training process.